Even more anti-differentiation or integration by substitution. Day 3. If we look at our goals, hopefully you're getting better at choosing the appropriate u substitution. Because I think once you have the u, the rest of the process, if you're nice, neat, and organized, is a lot more straightforward. Hopefully you're starting to identify when you're supposed to use in substitution to do antiderivatives. We're looking for chain rule stuff. Okay, first example. So when you see the indefinite integral of sine of x dx, you should think, oh, wait, I don't need any substitution or anything like that. We're just going to write negative cosine of x plus a constant. Pretty straightforward. But if you have sine cubed, and right after this, I'm going to do the indefinite integral of sine squared x dx. If you have sine cubed, sine to the 5th, sine to the 7th, what can we do? Well, let's think through this. I think it's good to think of what u is as well as what u is not. So instead of, going the direct way, maybe think through, because at least somebody is thinking, well, why don't we just do sine to the 4th x over 4? And, the answer is, well, let's take the derivative. You're good at derivatives. So just ignore what we're supposed to get for a moment. And the derivative, let's maybe do it over here. Pretend like you don't know, what we started off with. And just, okay, the derivative of something to the 4th power is 4 times that something cubed. And that something is sine of x, which has a rate of change of, oh, darn it. We forgot about the chain rule. So there's at least one way that, well, we might make an error. And so maybe we try to figure out what u is. Maybe u is sine of x. If that's not correct. If u is sine of x, then du is cosine of x dx. I don't know. It's sine of x times sine of x times sine of x. Or maybe it's, I don't know. Well, maybe u is sine of x. But how could you get a cosine of x? Doesn't really seem like it. So that doesn't seem right. Maybe u is, well, u can't be sine cubed, because then du is equal to 3 sine squared times dx. And if we have u replacing sine cubed, we don't have anything else. Dx is the only bit that's left. And so, maybe, and this is the case, maybe it's du that's sine of x. And if du is sine of x, that means u is some version of cosine of x, which is the case. Let me get rid of that, and then I'm going to animate what I already had written. And here's the hint. This sine of x dx, that is going to be du. So I guess u has to be cosine of x. But the other bit is sine squared. Can you turn sine squared into cosine? Yeah, we just do a Pythagorean identity. 1 minus cosine squared. And then, well, now it's a little more obvious that u is cosine. Du is negative sine of x dx. So we have these negatives, so we can make a direct substitution. And negative comes down, integral comes down. 1 minus cosine squared is 1 minus u squared. And this negative sine dx becomes du. From there, antiderivative is pretty straightforward. Negative u plus u cubed over 3 plus c, and replace with cosine. So we end up with negative cosine of x plus cosine cubed x over 3 plus a constant. And you can see if we did the derivative of negative cosine of x, we would get sine of x. If we did the derivative of cosine cubed x over 3, that would be 3 cosine squared over 3, chain rule times negative sine, and then, well, plus 0. And that may not look like what we started with, sine cubed. Dang, but is it? Maybe I'm going to factor out a sine. So if I factor out a sine of x, that's going to be 1, and then that's going to be minus cosine squared x, and 1 minus cosine squared x is sine squared x. Okay, I'm out of room, but that's definitely equal to sine cubed. Well, what do you do if you're integrating sine squared? Well, you know, we know u can't be equal to sine of x, because that would mean du is cosine of x dx. And if we rewrite that integral, well, we can break off one sine, but what we can't do is turn a sine of x into a cosine of x to get a dx, which also means we can't do what we did in the previous one and say u is cosine of x. We can get du is sine of x dx, but we can't turn the other sine into a cosine. And so what do we do? And the answer is, you remember power reducing. And power reducing formula is one of those things that comes up in trigonometry class that a lot of people forget about because, well, you don't need it really until you get to doing antiderivatives. So hopefully you can see, and I'm going to tell you where this formula comes from here in a sec. Let's just assume this is equal sine squared and 1/2 minus cosine of 2x over 2. Now we have, because, well, 1/2's a constant, and the antiderivative of 1/2 with respect to x is 1/2 x. And the antiderivative of negative cosine is negative sine, still with a 2x in there. But now instead of divided by 2, we're, dividing by an extra 2. So we're counteracting the chain rule, however you want to say that. And so that's kind of a weird one. And so how do we get that formula? Well, I think your best bet is not to memorize. Obviously, if you had memorized that, you would have had it memorized. So hopefully you know cosine of a sum of angles. Because if you do, I think this is the best trigonometry formula because you get a whole bunch of stuff out of it. So already you have cosine of a sum of angles. Maybe you need that, maybe you don't. If we put x and x in instead of like alpha and beta or pi thirds plus pi halves, something like that, we get double angle for cosine. So that's thing one off the bat. Right? So we already have a formula that might be useful in a different context or another formula we need. Okay, so let's call this, I'm just going to say, hey, this is double angle for cosine. Now, what we're trying to get is sine squared x equals some stuff. Right? That's, in fact, what stuff? We're trying to get sine squared equals 1/2 minus cosine of 2x over 2. The reason being, we don't know how to find the antiderivative of sine squared in that form. And so what we need to do, oh, wait, there's sine squared. But what we don't want to do, and I'll tell you why, we don't want to say sine squared is equal to cosine squared minus cosine of 2x. And the reason is, back here, if we can't do the antiderivative of sine squared, we also can't do the antiderivative of cosine squared because, well, that's not identical. By now you should know derivatives and antiderivatives of sine and cosine are pretty much the same, like 99% the same, right? All we have to do is deal with that negative. Okay, anyway, so we don't want to do that. Instead, what we want to do, because we don't want that cosine squared on the other side, we want to get rid of that cosine squared. And the way to do that is to replace it with 1 minus sine squared, Pythagorean identity. And then, oh, cool, we can just combine those sine squared. So cosine of 2x is 1 minus 2 sine squared. And now we're kind of good because we see cosine to the first power, which we can find an antiderivative for, and that constant 1. And so all we need to do is just kind of algebraically rearrange. Add 2 sine squared x to both sides, subtract cosine of 2x from both sides, and divide by 2. So sine squared is 1 minus cosine of 2x all over 2. And so what I wrote on the previous page was 1/2 minus cosine of 2x each over 2. Because then, you can do the antiderivatives of each piece separately. Okay, there you go. So that's why I think that's a really good formula. But wait, there's more. You can actually keep rearranging and get half-angle formula that, again, you may have memorized but probably forgot by now. So we'll take the square root of both sides, and the square root of The square root of something squared is really the absolute value of that thing. So we just drop the absolute value and make a plus minus. And if you're using half angle, you have to choose the correct sign based on what region we're talking about. Anyways, whatever. So almost there. And then what we do is, half angle formula, we're going to replace the x and the x, or really the cosine of 2x, because what we want is something in here. This is like cosine of an angle we know. So just think pi fourths or 45 degrees. And then that would allow you to find sine of half of that angle, sine of pi eighths, or 22.5 degrees or something like that. Okay, cool. Now, it's even better than that, just in case you're wondering. So we got a ton of formulas out, and then realized those were all for sine, but we could have done basically the same thing for cosine if we just, in this step, left cosine of 2x and cosine squared x and subtracted 1 minus cosine squared. Because then we would have cosine of 2x is equal to 2 cosine squared x minus 1. And cosine squared x is equal to 1 plus cosine of 2x all over 2, which is what you would do if you needed to do power reducing for cosine. You had to integrate cosine squared. In fact, we're going to do that right now. So there you go. If we're going to integrate cosine squared x dx, that means we're going to rewrite this as 1 plus cosine of 2x. Oh, that's weird. Over 2 dx. The thing that's weird, just with the darker background, I'm writing neater. Super strange. Okay, so the antiderivative of 1/2 with respect to x is 1/2 x. Antiderivative of cosine is sine. And that's still going to have the same input 2x. Now, if I took the derivative of sine of 2x, that would be cosine of 2x times a 2. I want a denominator of 2, so I need a 4 to counteract that chain rule. Don't forget your plus a constant. Oh, I already had that written out. I think it's better to kind of think along. Okay. And again, you could use substitution there, but you don't really need the substitution to deal with the 2x, hopefully. Okay. I don't want you to complete the whole process, but how would you deal with cosine to the 4th power? There are two good ideas. Maybe it's cosine x times cosine cubed x dx, or maybe it's cosine squared x times cosine squared x times dx. And, well, over here, remember, we can do the antiderivative of a single cosine. And we can do the antiderivative of cosine cubed. But let's see, how do we do cosine cubed? We change 1 minus cosine squared to 1 minus sine squared. And then, sorry, I wrote cosine squared because I'm thinking I have 2 cosines. So that would be cosine squared times 1 minus sine squared. And if you said that u is equal to sine, then du is equal to cosine of x dx. But you'd only be using one of them. You'd have an extra cosine left over. So actually we break it apart into this cosine squared version. So we would integrate and we'd write, did I write this already? No, didn't think so. Cosine squared x dx. And then that's going to turn into 1 plus cosine of 2x over 2 times a whole nother 1 plus cosine of 2x over 2. And you could write this as an exponent too. I don't know why I don't. I'm going to bring the 1/4 out front while I multiply. And 1 times 1 is 1. And I'm going to have 2 cosine of 2x's. But unfortunately, I have cosine squared of 2x. And I can find the antiderivative of 1. I can find the antiderivative of 2 cosine of 2x. But cosine squared of 2x, I have the same problem that I've had previously. Namely, I can't do the antiderivative of cosine or sine squared. So I have to use my formula again. So 1/4 will stay the same. 1 plus 2 cosine of 2x would stay the same. But here, cosine squared of an angle is 1 plus 2 cosine of double the angle over 2. And I'm leaving that blank for a second because, I don't know, experience tells me that might be confusing. You know, you might be realizing I made a mistake as I did. Inside here, the angle is 2x. So down here, we're doubling that 2x. And you're going to end up with 1 plus 2 cosine of 4x over 2. How would you deal with the integral of sine to the 5th of x dx? Well, it's just like sine cubed. There's just a little more algebra. So 1 of the sine squareds becomes 1 minus cosine squared. The other sine squared also becomes 1 minus cosine squared. And you have a leftover sine of x dx. And then to me, that's pretty straightforward, that cosine of x is u. Du is negative sine of x dx. We'll put in a negative, and we get the negative integral of 1 minus u squared times 1 minus u squared. The negative, the sine, and the dx become du, and we would just have to multiply everything out. But we get to some power rule stuff there, which is pretty easy to deal with. I think you can finish from there. So the next thing is, if you want to test yourself or if you're sitting in my classroom, we did this as a little pretest. The definite integral from 0 to 1 of x cubed times the quantity of 1 plus x to the 4th, all raised to the 5th power dx. So if you're playing along with my class, pause this, do this problem all on your own, like it's a quiz with perfect notation, and then I'll show you my stuff. I typed up all the results, or I wrote it out. I can't remember. Doesn't matter. And then next to that, I have rubric scoring, like the checklist of the things I think are best. Okay. Here we go. I realize that you're probably just waiting. So to me, it's pretty obvious. 1 plus x to the 4th is u, because I see the derivative of that involves x cubed. Now, not exactly x cubed, but I can just put a 4 and a 1/4 on here, basically multiplying by 1. And I end up being able to write a new integral, 1/4 of the integral from 0 to 1 of 4x cubed times 1 plus x to the 4th, all raised to the 5th power dx. And now I can make my substitutions. The 1/4 doesn't change. 4x cubed and dx became du. And of course, 1 plus x to the 4th to the 5th is u to the 5th. Why are the bounds 1 and 2? Because remember, we are going to take this 1, maybe we'll just do it here, is 1 plus 1 to the 4th. We took the lower bound 0, and we put it into x to the 4th, because u is 1 plus the x value to the 4th. Likewise, this 2 down at the bottom, that's the upper bound 1 to the 4th power added to 1. Okay, so from there, we are going to find an antiderivative, u to the 6th over 6th, and we're going to evaluate that from u equals 1 to u equals 2. And we'll substitute in there, pretty straightforward, 2 to the 6th over 6 with that 1/4 out front. And then we're just going to simplify. And I realize most of you will do 2 to the 6th, but come on, that's 2 squared, 2 to the 6th, and this extra 2 here. So you end up with 2 cubed over 3, but, whatever. Although I noticed yesterday in class when I was doing this, yeah, we can actually divide out a 3 here, but I'm not really worried about it. So here's what I would be looking for. Here's what you should check to make sure if you did this along with us. Did you copy the problem correctly? Then you should have u equals 1 plus x to the 4th written directly underneath that, and du directly underneath that, 4x cubed dx. Watch out for this dx in pink and this dx up here. For some reason, people forget those. So that's the first 2 points I'd be looking for. And whether you did it down here or not, I expect to see, and we'll put it up here because both are acceptable, one integral that still has x with a 1/4 and a 4. Mostly the 4 because I want you to be doing direct substitution. You know, this du says if you want a du, you need a 4x cubed dx. So make sure you have a 4x cubed dx. Okay, down here in blue, we want to see an integral in terms of u. The 1/4 is out there. And the point really we're looking for is when you change to u the first time, did the bounds change from x equals 0 to u equals 1 and x equals 1 to u equals 2? When you do the antiderivative, I don't think you're going to screw up u to the 6th over 6, but maybe you did. I also expect to see not just 1 and 2, but u equals 1 and u equals 2. The reason we do that is if you wrote an x equals 0 and x equals 1, you're constantly in that habit. You'd realize, oh crap, those are x's, and I'm supposed to be plugging in u's. We want to show the substitution, and we want to just get rid of all those exponents. Now, the last point I'm looking for in my class, no scratch work off to the side. Not crossed off, not erased, like there should be no scratch work. You should be able to do everything in the context of the problem. I hope that helps.